Okay, I'm going to get started. Hi, everybody. Welcome to ResinTech's online educational series called ROSE. This is a brand new initiative for us. It's a monthly webinar series that discusses water and wastewater related issues that matter most to you. My name is David Chesnick. I am the Global Director of Marketing for the ResinTech family of companies. And with me on today's webinar are Peter Myers, our Technical Director, Frank Da Silva, who runs our Western region sales here in the US, and I'm sorry, and Caitlin Clark, who's one of our technologists here. Frank and Caitlin are going to be working in the background to kind of curate some of your questions and provide answers along the way. We have quite a number of attendees on today's call, so we're going to try and move through this quickly because we know we value your time. We appreciate you putting it aside to learn a little bit with us, and we're going to try to get you out of here in about an hour. For those of you unfamiliar with ResinTech, we're a global manufacturer of water and wastewater treatment products and services. We're headquartered in Camden, New Jersey now, we're proud to say. We recently completed construction of the building on your screen right now. The solar-powered global headquarters. It's about 300,000 square feet between the two buildings that it occupies. And here are all the different products and services that we offer underneath that single roof, many of which come from ResinTech or Aries Filter Works, one of our other divisions, as well as ACM Technologies, another division you might be familiar with. Both those brands are going to be rolling under the ResinTech brand as the year progresses, and you'll hear more about that in the future. For today's webinar, I'd like to just quickly highlight some of the rules of the road. First, I'd ask you all to mute your microphones. There's a lot of people on this Zoom and we want to avoid collision. I'm going to ask you to refrain from using the hand raising feature on the webinar. I think we'd rather you use the Q&A feature. And as I said previously, Caitlin and Frank are going to curate some of those, and Peter's going to try to address them at the end of this webinar all at one time. The presentation itself is being recorded, and it will be available via our new website in the future. And we're going to be sending out a survey after the webinar to try to gather your feedback, as well as there'll be a QR code at the end as well that you can link to it very quickly. So if you have your cell phones on you, that'll be handy as we go along. So with that as a background and without any further ado, I'm going to turn it over to today's featured speaker, our Technical Director, Peter Myers, to talk about the removal of trace contaminants. Peter?
Well, good afternoon or good morning, depending on where in the world you are. I am the technical manager for ResinTech, and I have to confess, I've done hundreds of in-person talks. I think I've done 3 or 4 webinars. So this is a rather new format for me. I'm wearing a tie today, and this is the first tie I've had on in over a year, and I think we all know why that is. As I was getting ready for this webinar, I was thinking about ion exchange resin and how much resins have actually changed the world over time. You know, it was the 1940s when we developed the first real demineralization processes. And that allowed us to start making things like semiconductors, high pressure boilers, and high pressure steam turbines. And it really brought on a whole host of new manufacturing opportunities. Now, ion exchange resin as a source of bulk demineralization has been largely supplanted by membrane processes. But one of the best features of ion exchange resins is their ability to take out trace contaminants, to remove the needle from the haystack, or to take out a small amount of a trace ion out of a sea of ordinary salts. And I didn't want to do ion exchange 101. I wanted to do something a little bit different. And I thought about this principle of concentration difference, which permits a relatively simple but quantifiable way of looking at how resins really work. So without further ado, we're going to start the presentation. I'm going to turn my camera off because it distracts me, and I'll turn it back on when we get to the wrap-up stage. Let's see if I can do this without. Okay, good. So the agenda for today will be the uniqueness of water, followed by some basics of ion exchange and some ion exchange theory. And we just need a little bit of this as background before we get into trace contaminants. We'll talk about theory of trace contaminant removal and the principles of concentration difference. And then we'll wrap up and we'll be ready for questions. Sometimes we forget how unique water really is. And in part one, we're going to talk a little bit about the four basic elements, uniqueness of water, move into the way that salts and molecules dissolve into water, and then finally what the difference between bulk and trace contaminants is. Just a moment to reflect on the beauty of our planet. And I don't know about those of you who are listening, but I think all of us need to do our share to maintain the beauty of that planet, because if we don't, really bad things are going to happen to us. The original four elements, as told by our ancestors, were earth, water, air, and fire. These were the four basic elements that they felt made up the universe. And it's interesting because even at that time, water was very important, and that hasn't changed over time. Water is still the building blocks from which many other material things are made. You know, we're uniquely water, but most of our fresh water is in the ice fields, which are now melting. There's relatively little fresh water in lakes and rivers compared to salt water. And a lot of what is fresh water is not in the areas where we actually need it. So a lot of Earth's human population lives in areas that don't have enough fresh water, or in some cases don't have any. I grew up in the arid western part of the United States, and I love the desert, and there's no water there, or very little. And of course, to drive the point home, our bodies are 65% water, maybe more than that. But without water, we die within a few days. So water is an extremely important part of our environment, and I'm happy to be part of the industry that tries to take care of it. Water is also unique. It is not a molecule that behaves the way you would think it would. It's highly polar. The hydrogens are pulled to one side of the oxygen, and so the top of the oxygen atom has a very strong negative charge, while the bottom of the molecule, has a very positive, strong positive charge. That causes water molecules to bond together by hydrogen bonding and is responsible for much of its unique chemistry. For instance, water should really be a gas at room temperature. It should freeze at a much lower temperature than it does. Has very high surface tension, high heat of vaporization, which is good if you're driving a steam turbine. And it's relatively thick and sticky compared to other liquids that have similar molecular weight. It's also known as the universal solvent, and more substances dissolve in water than just about anything else. In fact, water picks up a little bit of contamination from almost anything that it comes in contact with. When salts dissolve in water, like sodium chloride, for the most part, they form ions. Salts aren't poisonous except at very high concentrations, at least most of them are not. And ions, if you're not familiar with the term, are simply molecules that have either gained or lost electrons. Ion exchange resins are used for a variety of purposes. The bulk ion removal, the removal of salts, include examples like water softeners, nitrate removal units, and indeed even deionizers, which was one of the earliest uses of ion exchange resin in bulk. But molecules also dissolve in water, and not all substances turn into ions. Some molecules are covalently bonded and the bonds are too strong to permit ionization. Others are ionized to some extent, but part of it remains molecular even though it's dissolved. Just a couple examples, and in future webinars, we'll talk more about some of these substances. For instance, sugar dissolves readily into water, but it remains molecular. Silica is molecular at neutral pH, but becomes ionized as a silicate anion at high pH. And carbon dioxide is often present in water in both molecular carbon dioxide and ionic forms, bicarbonates or carbonates. The reason for mentioning this is ion exchange resins in general remove only ionized substances. And quoting absolutes is dangerous. I used to say, well, we don't remove anything that isn't ionized, but I came across an application just a week ago where we are using a cation exchange resin to remove a molecular substance. So just be careful about absolutes and realize that there are almost always exceptions to every rule. We're going to move on to part 2 now, which are some basics of ion exchange. We'll talk a little bit about how important ion exchange resins are and differences between molecules and ions, some of the early ion exchange materials, ion exchange selectivity. And from there, we will have just a brief discussion of equilibrium and kinetics. So think about a world without cell phones or computers or the internet. That's the world that we would have without ion exchange resins. And the reason is that most of our electronics require very pure water, water that is not obtained by any other process except ion exchange. Our reliance on cheap and plentiful electricity also depends on ion exchange products, both for driving high-pressure steam turbines, and even if you have solar electric panels, those panels required very pure water in the manufacturing. We would also not have any way to remove many of the toxic contaminants from our drinking water. Now, some of those contaminants we added ourselves, some of them are naturally occurring, many of them are removed by ion exchange resin, and some are not removed by any other process. Almost all manufacturing processes depend on pure water for at least part of the equipment that was built. So what's the difference between a molecule and an ion? Well, both contain groups of atoms, but ions actually have an electron either stolen, they either steal an electron or they have an electron stolen from them. So the robber, the part of the atoms that grabs the extra electron, becomes anionic and has a negative charge. And the robbee becomes a cation. It lost a negative charge, so it becomes positive. When I was writing this up, I was thinking about an early movie. If anybody saw Forbidden Planet, that was the advent of Robbie the Robot. And then later there was the Lost in Space sitcom that was on for a few years. So if you're old enough to remember that, those were back in the 1960s. That just reminded me of that while I was putting the slide together. So ion exchange resins only remove ions except for the exceptions. Another picture, ion exchange process, where we see a negatively charged anion being attracted to a positively charged anion exchanger. And there's two things to take away from this. One is, that unlike charges attract, like charges repel. That charge barrier also prevents cations from entering the anion resin And on the other side, it prevents anions from entering a cation resin. So first, there were the natural zeolites, and this was the 1800s when they were discovered. And they discovered a process called base exchange, that certain soils were able to remove ammonia. And that was really the first ion exchange product that was ever discovered. That was supplemented shortly after by the natural aluminosilicates, the natural zeolites. Fast forward about 100 years, and not quite 100 years, we developed the synthetic aluminosilicates. They were pretty good softening medias. They were good cation exchangers, but they had a problem, and that was that they gradually dissolved into the water, releasing both aluminum and silica. Sulfonated coal that was soaked in concentrated sulfuric acid, was the first stable ion exchanger. And it was stable at pretty much any pH. You could soak it in acid, you could soak it in caustic, it didn't dissolve, it was pretty inert. That was followed by some of the phenolic condensate polymers. Those were the first weak base resins. Fast forward to the 30s, and we discovered that we could sulfonate polystyrene. That was the advent of the first softening resins. When we figured out how to chloromethylate the polymer, that allowed us to begin making strongly basic resins. It was also the basis for most of the chelating resins, because following the chloromethylation step, we could also aminate. The acrylic divinyl benzene polymers came last, and those were the first weakly acidic resins, followed by weakly basic and strongly basic resins. So today, almost everything that we use is based on styrene divinyl benzene with the balance acrylic divinyl benzene. The strong acid cation resins are exclusively sulfonated copolymer. The weak acid resins are exclusively acrylic divinyl benzene. And we have weak and strong anions that are mostly styrene DVB, but there's some acrylic DVB and a number of different amine functional groups. Moving on to part 3. Ion exchange theory, physical characteristics, selectivity, small and fast versus big and slow, crowding, and a brief note about units of measure. My daughter was about 4 years old. She came home from school one day, and she told her friend Matthew that Daddy worked in a smoke factory. I have no idea where she got that, but that was when I decided I needed to teach my family a little bit about what Dad did at work. And it's not your every average go to work type job. So ion exchange resins are plastic beads that take salt out of water and put other salts back in. And I think that "and" is just as important as the other part, that it is an exchange. It's not a complete removal. Something goes in, something comes out. If you've never seen them physically, they're solid plastic spheres, 0.5 millimeter in diameter. That plastic is functionalized. The solid cation becomes an anion resin. It's actually a solid acid, or a solid base becomes a cation resin. The solid phase has a mobile counterion of the opposite charge that's free to move in and out of the solid plastic. And that, in a nutshell, is what ion exchange resins are. Here's what they look like. On the left is a gel resin, and on the right is a macroporous resin. The gel resins are translucent. The macroporous resins are opaque. The chemical functionality is identical. So the way that they work is slightly different. The gel resins are generally higher capacity, and the macroporous resins are generally more durable. but as always, there's exceptions. So why does a resin prefer one ion over another? Helfrich was he was a chemical engineer who worked at Caltech a long time ago now. He attributed selectivity to swelling pressure. And indeed, the most swollen form of a resin is always the least preferred form. It's kind of a hard concept to wrap your head around, and a simpler theory is some ions simply fit better. Now, valence or number of charges is also important, not just because of selectivity, but because for divalent ions, selectivity changes with concentration. I was trying to put in a slide a little bit of an introduction for kinetics and equilibrium. And I saw this slide, you know, the big ones eat the little ones. And then when you Google that, you come up with another saying, the fast ones eat the slow ones. I don't think any of those are true all of the time. Nobody wins all of the time. So conditions that favor fast and small are short empty bed contact times and high ionic strength. And conditions that favor big and slow are slow flow rates and low ionic strength. But it all depends. There's no absolutes. This is one of the fundamental concepts of ion exchange, is that of selectivity reversal. And sometimes it's a little bit hard to explain, but divalent ions need two ion exchange sites because they have two electrical charges that have to be neutralized. In uncrowded solutions, divalent ions can find two adjacent sites, but when they become crowded, higher concentrations, that's more difficult. Think about it, if you're going to a theater with a friend and you want to sit together and you get there early when the theater is empty and you can find two seats that are adjacent without any trouble at all. But if you get there late and the theater is full, your chance of finding two empty seats right next to each other goes down. It becomes more difficult. And this is exactly what happens with ion exchange resins. At low solution concentrations, the divalent ions are greatly preferred. As concentration increases, selectivity for the divalent ion decreases, and in some cases actually reverses and is less than unity. Now, this doesn't happen with monovalent ions. Monovalent ion selectivity does not change significantly with concentration. To put it simply, kilograins suck. It's about as convenient as expressing the speed of light in furlongs per fortnight. Milliequivalence is simply the ion concentration divided by the equivalent weight. An equivalent weight is a molecular weight divided by the valence. It's so much easier to work with equivalents once you get used to them. We need to do this because when we talk about ion exchange resins, we're talking about number of charges, not just the weight of the ion, but the number of electrical charges. So for the record, 1 milliequivalent per liter is exactly 50 parts per million as calcium carbonate. 1,000 milliequivalents per liter is 21.8 kilograms per cubic foot. And a bed volume is 7.5 gallons per cubic foot, or if you're working in metric system, it would be 1 liter per liter. Ready for trace contaminants. The needle in the haystack. And this is the heart of the lecture. We're going to talk about a working definition, the principle of concentration difference, which is what this webinar is really about. some simplified mathematics, and I'm going to go through a number of mathematical exercises showing how an ion with equal preference is concentrated onto the resin, and even an ion with low selectivity is also concentrated onto the resin. So what's a trace contaminant? Well, as a working definition, it's a very small concentration of an ionized but undesirable substance. Generally less than 1 milligram per liter and less than 1% of the total ions present. The difference is that bulk ions accumulate to a significant fraction of an ion exchange resin capacity, but trace ions do not. That makes the throughput calculations for bulk ions complicated. Another reason is that bulk ions are often present in the new resins, while trace ions are usually not present. Removal of a trace ion and replacement with a bulk ion doesn't alter the water or the resin. Once we've made these assumptions, we can simplify the ion exchange capacity equation and make very simple but useful calculations about throughput capacity. Now, this is something I did just this morning, and I hope it goes over well. If it doesn't, I won't do it again. It's a way of trying to explain the difference between bulk and trace. So when there's no trace ions in the resin properties and behavior with respect to the trace ion are determined by whatever ionic form the resin starts in. So I got a resin bead that's pure white. It's all in its starting form. And it's going to behave with respect to the trace ion in a certain way. As I put a little bit of trace contaminant into the water and a little bit on the resin properties and its behavior with respect to the trace ion are still determined by the starting ionic form of the resin because it's almost completely still in that form. As I start to increase the trace contaminant concentration in both the liquid and in the resin properties begin to change. At first, the behavior is mostly determined by the starting ionic form of the resin. As we increase the trace contaminant still further, the properties become intermediate between the starting ionic form and the form of the trace contaminant, but the resin's properties and behavior are still dominated by the starting ionic form. We go a little further to the point where maybe we don't think it's a trace contaminant anymore, and that simplifying assumption that the properties and behavior remain constant is no longer valid. The resin properties are now in between that of the starting ion and the no longer trace ion, and the simplifying assumption is inaccurate. And eventually, from this point on, the principles of trace contaminants that being controlled by concentration difference no longer apply. The interaction between water and resin enters the realm of bulk contaminants instead of trace contaminants. If we try to use the simplifying assumption, our answers become wildly inaccurate. So, principles of concentration difference. First of all, we're assuming that the ionic concentration in the resin is much higher than the ionic concentration in the water. We're also assuming that at equilibrium, the equivalent fraction of the trace ion will be equal to the equivalent fraction of that ion in the water times the resin's preference for the trace ion. The trace ions remains a small fraction of the resin's total capacity. That way, the behavior of the resin towards the trace does not change very much. When these conditions are met, we can use a simplified calculation to predict the behavior. These simplified equations, I didn't make them up. They were first proposed by Bob Anderson. He was a chemical engineer at Diamond Shamrock back in the 1970s and early 1980s. So for our example, take a resin concentration, cation resin of roughly 100,000 milligrams per liter as calcium carbonate. If you're used to working in milliequivalents, that's about 2,000 milliequivalents per liter. Anion resin's a little less, about 70,000 milligrams per liter as calcium carbonate, or 1,400 milliequivalents per liter. When we're dealing with trace contaminants, we're typically talking about less than 1,000 part per million total dissolved solids. That's 20 milliequivalents per liter. And the examples I'm going to use start with 100 milligrams per liter in the water, 2 milliequivalents per liter. So at that point, the resin concentration is 1,000 times greater than the water. These are the simplified formulas. The fraction of the trace contaminant in the water times the resin's preference is equal to the fraction of that trace contaminant in the resin. That fraction times the resin's total capacity is the capacity of the resin for the trace. And the resin's trace capacity divided by the concentration of the trace in the water is the throughput capacity. In our first example, we're going to talk about metallium. Resin capacity is, that should be 2,000 MEQ per liter, sorry. Metallium concentration is 1 milligram per liter. And the TDS of the water is 100 milligrams per liter as calcium carbonate. The resin's numerical preference for metallium is exactly 1. So some of you may be wondering, what is metallium? Well, metallium is a mythical contaminant with an undefined mass or charge. It's named after Zalus Metallium, also known as the Lord Beastmaster, early Japanese anime. And I'm using it in this presentation as a substitute for any real ion. Any perceived disparagement of real ions is unintentional. So here's our first example. The concentration of metallium is 1. The TDS is 100. Preference is 1. So the numerical fraction is 0.01. 0.01 times the resin's total capacity, 2,000 MEQ per liter, is the resin's capacity for metallium, 20 MEQ per liter. Capacity divided by concentration is throughput. And in this case, it's 1,000 units of throughput, 1,000 bed volumes, or 1,000 liters of product per liter of resin. Keep that number of 1,000 in mind as we go through the next calculations. So the first principle of ion exchange, of trace ion removal, is that it's not necessary for the trace to be preferred. It's only necessary that there's a concentration difference between the water and the resin. So what happens to throughput if we cut the trace concentration in half? Okay, so now the metallium is present at 0.5 part per million as calcium carbonate. The TDS is a little bit lower because we just took out 0.5 milligram per liter of metallium. Preference is still 1. Fraction is smaller. Resin capacity is a little smaller, but because the concentration of metallium is also smaller, the throughput didn't change very much at all. In fact, the concentration of the trace ion is almost completely irrelevant as far as the throughput is concerned. Again, the concentration of the trace ion is almost completely irrelevant as far as throughput. What happens to TDS changes? So in this example, we left metallium at 1 milligram per liter, but we doubled the TDS of the water from 100 to 200. Formula, the fraction goes down. Since the fraction in the resin goes down, the resin's capacity for metallium goes down. But this time, when we calculate the throughput, because the resin capacity went down, but the metallium concentration did not, the throughputs dropped in half. And this is the importance of the bulk ions in solution. The TDS of the water has a profound effect on throughput. In fact, as a water treatment professional, in order to give advice about trace ion behavior, we need to know what the bulk ions are. We need that information every bit as much or more than we need to know what the concentration of the trace ion is. We don't need to have the trace ion preferred to have useful working volumes. And I'm going to use fluoride as an example because anion resin selectivity for fluoride is hugely unfavorable. Anion resin capacity is about 70,000 part per million as calcium carbonates, 1,400 milliequivalents, pretty typical. I'm going to use fluoride concentration as 1 milligram per liter as calcium carbonate. TDS is 100. The resin selectivity for fluoride is about 0.05, 20 to 1 against. We can use our same calculation. 1 milligram per liter divided by the TDS of the water times the preference. The numerical fraction is very small, times the concentration of the resin. And the resin capacity is pretty small. If you remember, some of the others were as much as 20 MEQ. In this case, it's 0.7. We run through to throughput, it's 35 bed volumes. Now that might not seem like much, but 35 bed volumes is still a relatively useful throughput capacity. So even a hugely unfavorable ion such as fluoride does concentrate onto the resin, and we can use the principle of trace ion removal and concentration difference to take unfavored ions out. So some of the common attributes, when we do this, many of these trace ions have huge throughputs. And the needle in the haystack, meaning that resin's got to come close enough to that contaminant to pull it inside. So kinetically, almost all trace ion removal is somewhat kinetically limited, at least compared to bulk ion removal. High ionic strength limits kinetics still further. So in general, when you're doing trace ion removal, you have to run slower than you would with bulk ion. Not always true, but it's often true, and it has to be considered in the design. Crowding reduces the apparent selectivity of certain ions. We have to be very aware of this. And volume throughputs are often high, which increases risk of fouling. These types of resins often have, thousands of bed volumes, and the opportunity for something to foul the resin is huge. This is a partial list of contaminants that ion exchange resins remove well. Vanadium, perchlorate, arsenate, chromate, lead, mercury, selenite, thallium, heavy metals, man-made radioactives such as iodine, strontium, cesium, radioactive antimony, cobalt, some of the naturally occurring radioactives such as radium and uranium. Now, uranium actually, because the selectivity is so high, can concentrate to the point where it goes beyond a trace, even though it's at a very low concentration in the feed. We can also take out organic anions such as PFAS, perfluorinated alkyl substances. From a standpoint of moving forward, our next webinar, I think 2 weeks from now, we're going to talk a little bit about bulk contaminants. It's Wednesday, March 17th. Keep an eye out for a registration link. I'm going to talk about ionic equivalents and equivalent concentrations, the selectivity equation that applies to bulk ion removal. Don't worry, at least for this webinar, no math is needed. A little bit more about resin theory, a little bit more about why the bulk contaminants are different than trace contaminants. And we're going to start in on some of the simpler bulk contaminant removal, the salt form exchanges, notably water softening and nitrate removal. We're thinking about potential future webinars. I wanted to throw some things on the screen just so you could see some of the thoughts that we've had. And all of you are free to let us know what you're interested in. If there's even a couple of you that would like this, we'll put them on for you. Deep dives into iron and manganese, radium and uranium, chromate. We're going to talk about separate and mixed bed DIs, external regeneration systems, multi-bed and deep bed systems, and some of the basics, things like water softening and nitrate removal, organic traps, how you store and use resin, how you dispose of it. Wrapping up, these are the takeaways we would like you to come away from this webinar with. When you're dealing with trace contaminants, the concentration of the trace is relatively unimportant. The TDS of the water, in other words, what the bulk ions are, is profoundly important. It's not necessary for the trace to be preferred to obtain useful throughputs. And with that, I think I'm pretty close to right on time. I'm going to turn my video back on and we're going to open this floor up for questions. Hi, everybody. Caitlin, did we get any questions?
Can resin remove 1,4-dioxane? First question.
First question is what?
Can resin remove 1,4-dioxane?
Dioxane is not ionized. And as a consequence, it is not removed by ion exchange resin, at least by any process that I know. It is fairly well removed by carbon, and it's even better removed by some of the carbonaceous adsorbents, one of which is made by charring cation resin, which does a good job. But there's several adsorbents on the market that are fairly effective for dioxane, and carbon is a backup. It's less effective, but it works.
And then when do you recommend gel type resins versus macroporous type resins?
We have a webinar on choosing a perfect resin, which we'll put on if people are interested. Very briefly, the gel resins are usually higher capacity and lower cost than their macroporous counterparts. So I would always consider the higher capacity, lower cost product first. And if it will work for you, that's going to be your most effective product, your most cost efficient one. Now, the macroporous resins have greater surface area. And in some cases, in fact, in most cases, they're stronger physically because they're higher cross-linked. But they also have lower capacity and they're more difficult to regenerate. Some types of resins are only available as macropores. Most of the weak base resins, for instance, are macroporous. Most of the strong base resins made with the higher amines, the specialty resins, and most of the chelating resins are also macroporous. And so in those cases, you don't have much choice. For condensate polishing and high flow rates, it's kind of a toss-up. The higher selectivity and greater physical strength is offset by the somewhat lower capacity and higher cost. And some customers prefer one and some prefer the other.
Since the ion exchange capacity depends on the number of charged sites available on the resin, can we assume the same capacity for different contaminants as long as they are the same valence?
No, because the capacity for a trace ion, the operating capacity of the resin is the fraction in the water times the preference. So even if the fraction in the water is the same, if the preference is different, then the operating capacity of the resin will be different.
For up to how much TDS would ion exchange be more favorable than RO for deionization?
That's a moving target. Back 30 years ago, it was somewhere in the neighborhood of 500 part per million TDS. Today, it's probably in the neighborhood of 200 part per million.
How is selectivity affected by the backbone structure, gel versus macroporous?
I've been doing this for almost 50 years, and all I can tell you is it's complicated. Selectivity starts with the polymer itself. And I'm a baby when it comes to making resin. I know a lot about resin applications, but the formation of the original copolymer is where selectivity starts. And my opinion is it has to do with the distribution and concentration of ion exchange groups.
Why, in some cases, do we need to put pre-filtration media ahead of softeners if we consider having an effective resin?
Well, we don't have to put anything in front of resin. We can just fill it up with suspended solids, plug it up, and then buy new. And ResinTech will love you when you do that. But if you have a contaminant that's going to concentrate in the resin, keep in mind, resins are both good coalescing medias, they are good filter medias, and they also concentrate a number of sparingly soluble contaminants. So if you have a sparingly soluble contaminant like iron, even if it's soluble in the water, if it precipitates during the regeneration and plugs up the resin bed or coats the surface of the resin beads, that resin's not going to work very well. The longer that the resin stays in service, the more problematic those contaminants in the feed become. If you want the resin to work best, you use it strictly for its ion exchange properties, and you take out these other contaminants upstream.
Can we briefly go over the throughput equation one more time?
Sure. All I got to do is find it. Let's see where to go. Okay, here. So the equivalent fraction of the contaminant in the water times the resin's preference for that contaminant is equal to the fraction of that contaminant in the resin.
You mentioned.
I'm not done yet. The fraction times the total capacity is the operating capacity. And that operating capacity divided by the concentration is the throughput.
You mentioned that with trace contaminant removal, the concentration in the water is not very important as long as the resin has none of the trace contaminant. What happens if the resin does have some trace contaminant present? How does that affect performance?
Well, ions that are accumulated at the bottom of the resin bed close to the exit are able to escape. So right off the bat, if you have some of the trace contaminant in the resin to start with, you're going to increase the leakage. You're also going to lose the amount of capacity left for removing trace contaminant coming in the top. And of course, the more trace contaminant there is in the resin, the higher the leakage will be and the lower the operating capacity will be. So the presence would be a parasitic weight on throughput and would also lead to increased leakage.
In the capacity equation, where does one get the preference number? So our K value.
Yeah, where do those numbers come from? There are various numbers that have been published over time. If you're lucky enough to have an old Dualite handbook, there are some numbers published. DuPont has some numbers. ResinTech has published some numbers in various papers. The hard way is you go in the laboratory and you equilibrate your resin with a liquid sample that has the contaminant of interest plus a counter ion, and you actually measure the selectivity coefficient. For the standard resins, they're pretty well established. For some of the specialty resins and some of the newer trace contaminants, the selectivity coefficients have never been measured.
How does particle size affect the performance, Gaussian versus uniform?
If the harmonic mean size is identical, it doesn't. If the uniform particle size resin has a smaller harmonic mean size, that means it has more surface area, which means it has faster kinetics. And in cases where kinetics wins, where the fast ones beat the slow ones, or sorry, the slow ones beat the fast ones, a uniform particle size resin with smaller harmonic mean size would beat a Gaussian resin. The problem with that, when you make a resin more uniform, you have increased void volume and lower volume capacity. You have less plastic in a given volume, and therefore you have less capacity. So you're offsetting the faster kinetics against the lower volume capacity.
Can we reduce TOC or AOC with resin, and if so, which type?
As long as the organic is ionized or partially ionized, we can remove it with ion exchange resin.
And the last question I have here is, the removal of PFAS comes with the question that given the large number of molecules in the family of PFAS chemicals, which ones are most likely to be successfully removed by resin, I guess, versus maybe carbon?
So we know some of those answers. The 8-chain PFAS chemicals and the sulfonates are more readily removed than the carboxylates. So PFOS would be removed better than PFOA. As we begin to reduce the number of carbons in the chain from 8 to 6, and some of them now are 4, it becomes more difficult for both carbon and resin, but it probably favors resin to some extent. When we get to the 10 carbon chains, I think carbon is probably better. But there's, every year we have more PFAS chemicals that are on the list, and only the 8 that were studied in the early days are really as well understood. There's still an awful lot to be learned about PFAS.
Okay, that was the last question I had on.
Okay.
Thank you, Peter. Peter, can I ask you to put up the slide that had the future potential topics on it. There's a
Sure.
QR code there. I want to show one more time to our attendees that are left.
Here.
So folks, if you have your cell phone with you, you can scan that QR code while it's on the screen. And that'll lead you to a survey where you can give us your feedback on this presentation that you just experienced. And also when you click to the next page, there's a whole long list of basic and advanced topics. Tell us which ones you're interested in, and we're going to kind of move with the democratic point of view on this and prioritize the ones that get the most votes. As Peter said earlier in the presentation, our next seminar is going to be, or webinar is going to be on March 17th at the same time, and it will be on bulk contaminants this time. And then after that, we're going to go probably on a monthly, perhaps bi-monthly basis, and take some deeper dives into some of those topics that you'll see on that list. So I certainly encourage you to go and fill out that survey and give us your feedback, and feel free to share these invitations or reach out to us at webinars@resintech.com, or reach out to your sales rep if you have any questions. This seminar has been recorded and it will be available on our website in the weeks ahead, and I'll send out a link for that. And if you would like a copy of the presentation, you can also reach out to us at, again, webinars@resintech.com, or reach out to your sales rep, and we're happy to wrap it up and provide it to you as well. So we appreciate your time attending today. As promised, we were able to get it in at just under an hour. Thank you very much, Peter, for all your hard work, and Caitlin and Frank for curating our question and answers along the way. Have a great day, everyone. We'll see you in 2 weeks.
Okay, thank you, everyone. Bye-bye.